This study investigates the effect of infill pattern on the bending strength of 3D printed parts. As 3D printed parts have become incredibly common in industry, finding the most efficient percent infill is crucial for optimization. This research is useful for anyone who uses 3D printed parts. The parts tested in this study could be used in brackets, casings, supports, or other load-bearing applications where strength and efficiency matter. The overall approach to obtain the data was to clamp a series of 3D printed beams to a table with a LVDT sensor attached. The sensor measures the deflection on the beam as weights are added to the end of the beam. This approach was determined to be suitable based on the comparison of the calculated Young's modulus values after sufficient data was collected. Industries like aerospace, automotive, and medical devices rely on strong but lightweight structures, and understanding infill strength can help them make better design choices. 3D printing has become increasingly common in industry due to the ability to manufacture 3D printed parts quickly. This research is useful for engineers, designers, and manufacturers who use 3D printing to create functional parts. The results of the research can help to create parts that are stronger and lighter, allowing a more efficient use of materials. Some elements of the broader problem with 3D printed parts are infill pattern, infill percentage, direction of force, such as tension, compression, or bending. We decided to focus on comparing 3D printed beams with different infill patterns of the same infill percentage of 10%, all in bending. Other methods of testing the strength of 3D printed parts include testing its strength under an axial load in either tension or compression, or using a strain gauge to measure the bending of the beam. The bending deflection experiment was chosen due to its repeatability and its many real-world applications. The assumption was made that 3D printed parts were placed in bending more often than in axial tension or compression, thus a bending test would be more informative.
The 3D printed beam is fixed at one end over here. The other end, the LVDT rests upon. There is a notch where it sits in to ensure that there's no sliding from the LVDT. The weight is hooked beneath this, and the LVDT is connected to the computer, where the voltage is obtained, and from the voltage, it's been calibrated to determine the deflection of the beam.
For this experiment, the deflection and the angle of the fixed end are assumed to be 0. The length of the beam is assumed to not change due to the deflection. Many steps were taken to minimize error in this experiment. The 3D printed part was designed to minimize error with a notch for the LVDT to sit in to avoid slipping, a hook to ensure that the load is placed in the same spot every time, and an extension to make sure that each beam is fixed at the same point. Some of the weaknesses of our data collection process involve the bucket, the table, and the LVDT itself. The bucket that was used to apply the weight sways back and forth, changing the beam deflection. The table on which the LVDT rests shakes. The LVDT is long enough to predict Young's modulus, but not long enough to measure the beam to failure. The results of the experiment show that the stars performed the best and the Archimedean chords performed the worst. This was determined by comparing the calculated Young's modulus for each of the patterns. We predicted the honeycomb pattern to perform the best based on knowledge that honeycomb patterns are commonly used in designing. We also predicted that the Archimedean chords pattern would perform the worst because the lines are perpendicular to the length of the beam rather than parallel. The latter prediction was correct, but the best performing pattern is the stars. One potential weakness that we tried to mitigate was the lack of significant data based on the design of the 3D printed beam. To combat this, we compared data collected from beams that were 9 mm thick to data from beams that were 5 mm thick. After determining that the data for the 5 mm was more applicable, all the beams were redesigned to be 5 mm thick, and the tests were redone. The statistical tools that were used in the uncertainty analysis were the student's table to determine the error on the LVDT sensor after it was calibrated, the uncertainty associated with the length, base, and height of the beam that was used in the experiment. The uncertainty value associated was used for the Prusa 3D printer. For the X and Y axis, this uncertainty value was 0.3 mm. For the Z direction, the uncertainty was 0.1 mm. The uncertainty of the deflection is equal to the uncertainty value of the LVDT sensor. The calculated uncertainty of the calibrated weights in the lab is 0.4% of the mass's weight. Refer to the Uncertainty Analysis Appendix, aka pause the video, for an in-depth exploration of the analysis. In conclusion, the order of strongest designs from greatest to least is stars with a Young modulus value of 1.594 gigapascals with an uncertainty of 0.061671 gigapascals and a confidence of 95%. The patterns that performed the best in order from greatest to least was squares, honeycomb, triangle, gyroid, then finally Archimedean chords with the Young's modulus value of 1.2769 gigapascals with an uncertainty of 0.0538 gigapascals and a confidence of 95%. The other patterns, all of their Young's modulus values fall in between this range. Once the mass of the beam is divided out, the efficiency of each pattern from greatest to least is in the same order. Note that the Young's modulus values are not exact for each pattern. These calculated values are strictly relative to this experiment, as they allowed us to determine which infill pattern is stronger relative to one another. This claim is validated by further testing with different sized beams, aka the 9mm beams. The thinner beams, regardless of pattern, had a higher Young's modulus value than the thicker ones, but relative to one another, the differences in Young's modulus values between the various patterns were still the same. To further prove this claim, more testing can be done comparing variations in the beam design to see if the relative differences are still the same. One alternative method that can improve data collection would be to use a strain gauge instead of the LVDT. The gauge would collect broader data as well as data for breaking point. Overall, we are satisfied with our decision to use the LVDT as it was more appropriate for the plastic beams. Different design decisions that we discussed included using a different table or setup. We used a height adjustable table that made setup easy, yet this adjustable table wasn't very stable. Anytime that the table was bumped or vibrations were caused by dropping items or footsteps, the LVDT would pick up on those vibrations. This led to slight errors in the data. We could get more accurate values with a better setup that included a more stable table. Another design decision that we decided was to use a suspended weight versus force applied from above. By suspending the weight below the beam, we were able to control the direction in which the force was acting. Since the weight was suspended from a single point, the only force acting was gravity, which only acts in one direction. This simplified the math needed to calculate forces, reducing the potential for error propagation. The last design decision that we made was the beam thickness. We decided to use the 5mm thickness beams instead of the 9mm thickness beams to increase the flexibility. This allowed for better observation of the differences in infill pattern. If the beam was too thick, the differences in deflection wouldn't be enough to gather significant data. The uncertainty analysis included multiple areas of our experiment. The uncertainty of the deflection is equal to the uncertainty value for the LVDT sensor, which is 0.4%. For the 3D printer, the Prusa 3D printer, for the X and Y axis, the uncertainty value was 0.3 millimeters. For the Z direction, the uncertainty was 0.1 millimeter. The scale to measure the weights had an accuracy of plus or minus 0.005 grams, and the calculated uncertainty of the calibrated weights in the lab is 0.4% of the mass's weight. The goodness of fit for each set of calculations is represented by the R-squared value on each graph of mass versus deflection. All of these R-squared values are above 0.99, meaning that it is a very good fit. The theoretical uncertainty and the empirical uncertainty values have been discussed and are also shown on the S-math uncertainty analysis. We concluded that our observed uncertainty values are similar to what our predicted values were because our uncertainty was almost negligible. Both the empirical and the theoretical uncertainties are agreeable.